Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. It's my great pleasure to welcome Colin Jackson to come here and interview with us. Colin is interviewing with my group, the security group, for either a researcher or postdoc position. Colin is a PhD candidate from Stanford University. He has been publishing prolifically in the area of web and browser security. And actually, Colin also interned with us as well as, worked with us for quite some time. And Colin also worked on Chrome as a developer, as a full-time developer as well as part-time developer. And he's also been consulting for many
startups,
potentially successful startups in Silicon Valley. So Colin will tell us about his dissertation on securing the web platform.
Thanks, Alan. Well, it's great to be here. I see a lot of familiar faces, people I met during my internship here in summer 2006. I was working with Dan Simon on anti-phishing research, and then met Helen, and we got really interested in treating the browser as sort of a operating system, as a platform for building applications, and it's really worked out well for me. We wrote a bunch of papers after that internship, and I guess culminating in the SOSP paper that I wrote with John and Helen. And I think a lot of my research since then has been inspired by ideas that we were kicking around while I was here for the summer. So I really am glad that I had a chance to meet everyone. So I'm an optimist about the web. We hear about all of these horrible attacks that are going on the web every day, but I think fundamentally it's becoming an extremely useful platform for building the really compelling applications. You're seeing web pages are becoming more interactive. People are making more use of JavaScript, of Flash, lots of technologies that are bringing sort of near to desktop experiences. And at the same time, you're seeing people getting more interested in software that doesn't ship on a life cycle of 4 years, but rather on a life cycle of every few hours, or every week you can push out a new update to your users. They don't have to agree to the update. They don't have to have their update be managed by some IT staff. The web page simply just runs the latest version, the latest and greatest that the website has to offer. And so that allows a much faster iterative cycle where you can be much more in connection with your users. You can immediately see the effect of changes in the application UI. So I think there's a lot of advantages to seeing programs move onto the web and web pages becoming more exciting and dynamic. So how do we secure the web as a platform for applications? The browser security policy, it was essentially, I think, born in 1996 when Netscape introduced JavaScript. And this is when cookies were also being introduced. And so you see a lot of the decisions that we're having to live with today are a result of the very initial policy that Netscape came up with. And ever since then, all the decisions that we're making are being informed by backwards compatibility with existing applications. And so it's very you have to be very delicate about the changes that you make to browser security policy, because you don't want to break any existing websites, or people will stop using your browser. So I think that the security policy was really designed when browsers didn't have multiple tabs. Users typically had one browser window open at a time. And each web page that they went to, typically that web page was providing all of the content that they were interacting with. Maybe some of the images were coming from different servers, but for the most part, you were having one principal that the user was interacting with, and you had to design your security model around that. So the goals, if you look at security papers from 1996, were very much about how do you protect the file system from a rogue Java applet. Those were sort of the security problems that we were facing. But if you look at the web today, you have lots of tabs open. you have lots of different principals that are contributing content to a particular page. So you have these Flash movies that are being brought in from different domains. You have these iframes that allow one web page to import content from another web page. All sorts of different communication and mashup features are being added to browsers. And the users are going to have lots of these concurrent sessions going on. So you might be logged in at multiple sites. And this adage of, oh, you should always log out of one site before you start your session in another is really not realistic for the kinds of browsing patterns that we're seeing today. So I think that there's a new kind of security model that you need for thinking about users who are browsing in this kind of a web. So this is an idea that I've been trying to develop at Stanford called the web attacker threat model. And it's basically a set of assumptions for what we're going to give the attacker. And if your feature is not secure in the web attacker threat model, it's not a very useful feature because the web attacker is an extremely conservative set of assumptions about what the attacker can do. So first we're going to give the attacker a web server. It's extremely easy to get a web server today. You just find a hosting company and you pay them a little bit of money. Or you can set up your own. We give the web attacker a domain. And because you own the domain, the certificate authorities are willing to give a certificate to the web attacker. So we're not going to make the assumption that certificate authorities will only issue certificates to good people. We're only going to make sort of the domain validated assumption about certificates. So the certificate authority is confirming that the attacker does actually own this domain. And then the most critical part of a web attacker threat model is that we assume that the attacker gets an introduction to the user. So you can imagine trying to design a feature that works as long as the user never goes to a bad site. And if you had a whitelist of all the good sites on the internet, maybe that feature would work. But in reality, users are constantly interacting with bad content. And so we want to design the browser sandbox to be robust in that model. So these are the basic set of assumptions. And I'm going to talk a little bit later about how we might want to adjust these for particular features where these set of assumptions don't make sense. So in introduction, basically, the attacker needs to get their attack code to run on the user's browser. The way the web works is it's a pull model. The user has to go to a web page before the web page can interact with the user. And so in order for us to reason about the security features of the browser, we need to assume that the attacker got their code onto the browser somehow. Otherwise, the attacker could never do anything interesting to the user. So here's the really key thing about the web attacker threat model, is we're going to be conservative, and we're going to make sure that we're not going to make the assumption that the user is confused about where they are. So why do I say this is a conservative non-assumption? Because if you have a security feature that doesn't work, even when the user is not confused about what's going on, they actually understand how to read domain names or how to use extended validation, then there's no way that you can build a user interface on top of it that the user will be able to use correctly, because the browser itself is confused about what's going on. So there's a whole other body of research, some of which I did at Microsoft, which is how do you make sure the user isn't confused about what principal they're interacting with? How do you let them know, oh, this is the real bank website, and this is some other fake imposter bank website? I think this is a really important research problem. But there's no way that we can really make headway on this problem if the browser itself is confused about what's going on inside this rectangle of content. So what these security indicators in the browser are telling you is, here's the domain that was in charge of filling this rectangle with pixels. But what pixels appear there need to actually be under the control of the Bank of the West. Otherwise, there's nothing that the certificate UI can do. So this is sort of an attempt to separate out separate areas of research in browser security. So if you're a web attacker, you can think of it intuitively as some other window or tab that the user visited and then forgot about. And now they're trying to do something important. So whenever you're looking at a web feature, always assume that in the background there is a window that's got malicious code that came from the attacker, and it really wants to attack your session with a site that you trust. The user is not confused about where they are. But so the attacker wants to do things like overwrite the pixels of this area. They might want to know what the user is typing into the password field. They might want to attack the storage that's associated with this principal. So in a browser, you can store cookies, and there's even a local storage database now that's associated with a particular principal. In this case, the URL of the site determines the principal that the cookies and local storage use. So the attacker wants to get access to that storage. They may want to know what you're doing in this other window. They want to know what you're clicking on, what you're typing in. And another resource that the attacker might want is the IP address of the user that's accessing this web page. So at Microsoft, you're probably familiar with the idea that some web pages are not accessible to the outside world. You have this firewall. You have lots of interesting web pages that live inside the firewall. And then you have web pages that are external that everyone on the web can access. So you should be able to go to a web page in one tab and have this be an external evil web page. And that web page, you're not confused about what web page that is. But that web page wants to use your IP address to connect to a website that the attacker can't directly connect to because of the way that the network connectivity is set up. There are web pages inside your firewall that the attacker needs your browser in order to connect to. Using your browser as a proxy is essentially into the firewall. So these are some different types of resources that you have in your browser that the attacker might want to gain access to. So I've looked at all of these different resources and tried to find cases where the web attacker might be able to jump in and steal something that the user has. So being able to access the pixels and keystrokes while you're on the bank website, that's something that Mashup OS was trying to solve. And that's something that I have a question. Yeah.
So it seems like it's missing another bullet, that is the memory, which is the DOM.
That's right.
So the pixels can be separate from, pixels is like the display.
That's right. So the storage, you can think of it as being both in-memory storage and also the persistent storage in the browser. And there are many other types of resources. These are just 5 that I've written papers on. And I think there's a lot more opportunities for applying the web attacker to things that you might want to steal from the user. So I'm going to talk about this in detail today. I'll also talk about this one. Briefly, right now, the way that the browser renders hyperlinks allows web pages to determine whether you've been to a particular URL or not by the way that a hyperlink renders, either purple or blue. So we looked at how a web attacker might use that to determine what you're doing in another window and proposed a solution for that. And also, there are some tricks that the attacker can play with DNS that allow a web attacker to essentially hijack your IP address and use it to connect to resources inside your firewall. So we've been working on that problem as well. But I'm going to talk about the first 3 next. So here's an outline for what I'd like to talk about. First, I'm going to talk about how do we understand whether this web attacker threat model is realistic. How expensive is it to get an introduction? Are there large-scale attacks that are possible just by setting up a web server and trying to attract users to it? And then I'll talk about how we take various web features, analyze them, and find vulnerabilities, and then propose solutions that get deployed by vendors. The deployment problem is a particularly hard problem in the web because of this backwards compatibility issue. And then I'll talk about different additional capabilities you might give the web attacker if you want a feature that's a little bit more secure, a little bit more powerful. So one potential approach to the web attacker, you know the web attacker is this website out there that's got some evil JavaScript code on it. You could just say, we're going to find all those bad websites. We're going to categorize them as being bad and throw up a warning if the user ever goes to that website. And there's actually been a lot of work in trying to figure out which websites are trying to attack you and which websites aren't. Google's been building up this big database. There's also the phishing filter in Internet Explorer that try to warn you when you go to a bad site. And I mean, this is a warning that I took just a few days ago on a real government website because the attacker had injected some JavaScript code via cross-site scripting into the government website. And that evil JavaScript code was trying to execute various types of malware, various types of attacks. So the problem with trying to blacklist all the content on the web that's evil is that it's just the barrier to entry is so very, very low that the attacker, if they found this warning on their site, wouldn't have to go through very much effort in order to set up another one and another one. And you could keep doing this with stolen credit cards until the blacklist just had to store huge amounts of content in the browser in order to warn the user in real time when they went to one of these bad sites. And the spider that's going out and crawling all the bad sites might see the bad JavaScript, but not be able to find it in time, or the website might serve up different JavaScript to the spider than the actual user who's using a real browser. So I think this is an important approach. I think it works better for phishing and malware than it does for cross-site request forgery and other types of weak web attacks that work in the web attacker threat model. So I said that setting up a server is really cheap. You can pay $10 and get domain and hosting. You can get a domain-validated SSL certificate for $0. We found a CA that will just, by virtue of you owning that domain, give you SSL. So that's why we assume that the web attacker can talk over the HTTPS protocol. But we weren't sure how much it would cost to actually get introductions to the user. And this is important because we need to figure out just what the scale of an attack might be if an attacker knew about a vulnerability in the browser. So we ran a series of experiments at Stanford where we used ad networks to try to test our attack code. We wrote some evil JavaScript that used some vulnerability in the browser. And then we found an ad network. We placed an iframe on that ad network that ran our attack code and checked to see whether it works. You're probably wondering how I got this past the IRB at Stanford. And the answer is that we only attacked ourselves. We were trying to bypass the browser's security policy, the same origin policy that prevents you from attacking other sites. So we set up 2 servers at Stanford. And essentially all we did was try to take some data from one server with some code that was served by the other. And so this way, we weren't harming any other websites on the internet. We were only running the test attack against ourselves. So there was nothing that we could steal. But we were able to demonstrate the viability of the attack with our attack code that was on the user's browser. And so what this graph shows is the amount of time that we had on the user's browser while some ad was showing. So this is an example web page. It's a news site. This is an example of the iframe that we had. You can't see it, but there's a bunch of JavaScript running in this iframe while you're reading the news. And that JavaScript is running the experiment to find out whether or not the attack worked or not. So what we found is that a lot of users navigated away very quickly after 1 or 2 seconds. They clicked on the article that they wanted to go to, and our ad was shut off. But there were a lot of users who stayed there for days or even weeks. And I think that this is really a testament to the fact that users keep a lot of tabs open, and they don't reboot very often anymore. And there's really no reason to close a tab unless you need to restart your browser. And so if you're a web attacker and you want to do an attack on a long time scale, $1 will buy you 2,000 impressions. So if you spend $1,000, you can get 2 million impressions. And that's actually a large number of browsers. It's enough that you could get exposure to a lot of browser vulnerabilities if they're only specific to a particular platform. So this is understanding whether or not an attack works and how many different browsers you can hack at once. But what if you want to run an experiment that determines whether or not a security feature is working? Yeah, go ahead.
So are a lot of the attacks out there actually done through the ads? So I understand your methodology. Mm-hmm. Is this how most attacks are done? Is like a common way for attackers to basically spread out their evil JavaScript code?
So there's actually a big business in trying to determine whether or not an advertiser is serving up evil iframes or not. This was a big problem for MySpace. Several times now, someone has taken out an iframe on MySpace and then used it to try to exploit ActiveX or some other browser plugin vulnerability to install malware on the user's machine. And this actually got viewed by tens of thousands of users before someone realized what was going on and shut it off. So I can give you some news articles that talk about this attack happening in practice. But there is evidence that real attackers are looking at this model and are finding it to be sort of financially attractive. $1 for 2,000 users is pretty good, even if your attack only has a 1% success rate. So we can also use this sort of ad network methodology as a platform for experimenting with different browser security features and figuring out how they work, treating the web as sort of an ecosystem rather than as a particular product. Because there are lots of different browsers out there, lots of different versions of those browsers, lots of different configurations. You've got firewalls, all sorts of different things affecting the HTML that people view. And so you might think that a particular security assumption holds on the web, but without actually testing it, seeing whether or not the browser security policy is being enforced correctly, you can't know whether or not it works the way you think it does. So you can test your hypotheses on a large scale like this. So we had a hypothesis about how the browser refer header worked. We wanted to test it, so we got about 200,000 users to run our JavaScript code just by virtue of displaying our iframe, and came up with some very interesting observations about the way that browser refers are handled. We had a hypothesis that the browser blocks the refer when you have an HTTPS page requesting an HTTP image. And we found that to be true most of the time. But what's interesting is that the refer header was also being blocked for HTTP to HTTP about 3% of the time, which is a significant fraction of the time. And we did some more experiments that found that that blocking was not happening over HTTPS. By the way, X and Y here are just two servers that we set up. So if you see X connecting to Y, that means the refer was X, and the server that you're connecting to is Y. So we found this interesting observation that when you have HTTPS requests, the refer is very unlikely to be blocked. But it's likely to be blocked if you have HTTP. And from this, we formed our hypothesis that most of the refer blocking that's going on in the network is happening as a result of proxies and other things that live outside of your computer and only have access to your HTTP traffic. They have a hard time modifying your HTTPS traffic in transit. So as a result of this experiment, we made a bunch of recommendations to vendors about how they should handle the origin header proposal, which is a new proposal for a replacement for the refer header. And so we're trying to understand what privacy problems do people have with the refer header that causes them to block this, and how can we design a new header that provides the security that people want from the refer header without having all of the privacy problems. So I'll talk a little bit more later about why you might want to use the refer header to prevent attacks. So anyway, this is the measurement approach that we've taken at Stanford. And now I'd like to talk a little bit about how we've actually tried to find vulnerabilities and features in the web attacker threat model now that we understand that the web attacker threat model is sort of a realistic thing for an attacker to use. So here's a very simple web attack. The user goes to a login page. And you can't tell, but there's an iframe on this page. The iframe is the login box, because this is a module that's used on multiple Google properties. So right now, it looks like the user's only interacting with Google. You've got the security indicators that are all in the right place, and they say Google on them. And so there really doesn't seem to be any interaction with some untrusted third party. But in the web attacker threat model, we don't just look at this one window. We have to assume that the user has lots of windows open. They're all sitting around in the background. And the attacker at any moment might try to jump in and steal some pixels or keystrokes from this page. So here's how the attacker might do it. They want to replace this login frame with an evil login frame, so that when you type in your username and password and click sign in, it'll submit the password to the attacker instead of submitting it to the to Google. So what the attacker might do in some other tab in the background is use the window.open API. Essentially, they name the frame that they want to access, and they pick a URL that will populate this with content that's controlled by the attacker. Now, the browser has this mixed content warning system, which tries to warn you when you have an HTTPS page rendering content from an HTTP URL. So this is why it's important that we make this assumption that the web attacker can get an SSL certificate. Because if they can make sure that this iframe will still be served over HTTPS, and the user won't get any warnings telling them it's a bad idea to log into this frame. So once the attacker has replaced that frame with their own content, you'll never know that you're actually talking to the attacker when you type in your password. Yeah?
So this is an HTTPS URL. So how is the attacker injecting the iframe?
Right. So the browser has this window.open API that allows you to name a window anywhere on your system. And you specify a new location for that window. And this API is designed to be cross-origin. So you can name a window that's not under your control. And the browser is supposed to navigate that window to a new location. It's a very dangerous API.
But they just bought the ad, right?
Yeah, so how did the attacker get introduced to the user? Well, the web attacker threat model says the attacker gets an introduction for free. In practice, what they're doing is you've got some tab open underneath this one where there's an ad. And the ad is
a script.
so the ad, yes, so it's an iframe that has actual JavaScript running. We've looked at ad networks. About half of them limit what kinds of content you can put in the iframe. Sorry?
Also, the browser might do it, might limit JavaScript within an iframe.
That's right. So the security restricted flag on iframes, for example, is a Microsoft proposal that would allow you to limit what can happen inside of an iframe. There's some effort underway to standardize that in HTML5 so that other browser vendors can adopt it as well. So the problem with limiting what can go on in the iframe is that some of that functionality is intended. It may be that the ad provider actually needs to run some JavaScript to figure out which ad to show on your system. And so there's a trade-off there. And for the moment, the sort of finance aspects of advertising seem to be winning over the security aspects. So I haven't seen a whole lot of people using security restricted yet. Yeah?
So just a clarification question. So here you have a malicious ad that's embedded in this page. Is that ad hosted across the iframe, or is it hosted, or is it just an inline script?
So the ad providers that we've looked at typically put your ad in a cross-domain frame. So they have some throwaway domain that they don't care about. So this is, Boston Metro News. Often what happens is Boston Metro News will iframe the ad provider, and then the ad provider makes a second iframe to some domain that they don't care about. And that's where your actual ad lives. So it has no privileges to the browser other than living at this strange domain and the ability to run JavaScript in your browser.
So the next question is, such an ad being running across the iframe, how can it, what today's browser is actually doesn't really allow this kind of cross-domain navigation. How did that work?
Yeah, so it used to be that this attack worked, and it worked in almost every browser. The IE team independently fixed this particular issue, but unfortunately, if you had Flash Player installed, they hadn't gotten the memo that this is a bad thing. And so they still allowed you to navigate any window on the system across origins. There was no origin checking going on when you tried to make a navigation. So what we did is we contacted all the vendors and said, look, this attack is bad, and we provided a bunch of different variants on the attack to show why you might want to lock down this API. And we got everyone to agree. It was a lot of work, but we got everyone to agree on what's called the descendant policy. It's actually based on IE. That says you can navigate a frame if you control a frame that is one of the parents or grandparents of that frame. So if you want to navigate this frame, you better be in control of google.com. You don't actually have to be the direct parent of this frame, but you need to be in the same origin as this one. And so we came up with some arguments for why that policy made sense based on pixel delegation. The idea that if you give someone some pixels, you can take them away at any time. And so that's why that got adopted. So this is an example of the web attacker trying to steal your keystrokes. And the key assumption that we had to make was that you weren't just interacting with this page. You had some other guy in the background that was trying to jump in. So let me give you another example of a web attack. Any questions about this before I move on? OK, so let's talk about cross-site request forgery. I'm sure this is a topic that's near and dear to some of our hearts. So basic cross-site request forgery attack, the user gets introduced to the attacker, because that's how a web attacker works. And the web attacker is going to create an HTML form that's going to submit some HTTP requests to a target server. And in this case, we're relying on this fact that users keep concurrent sessions open with a lot of different sites at the same time. And so they're already authenticated to this bank website using cookies. So the attacker can automatically in JavaScript, without any user interaction, submit this form. So they serve up this HTML document. The HTML document submits the form to the bank website. And then the bank sees that the user appears to be trying to transfer some money into the attacker's bank account. So because the user is already authenticated using cookies, the attacker allows the request. This is a very basic CSRF attack. So we'd like to prevent this attack. But before I talk about how to prevent it, let me describe a variant on it. This is something that we discovered at Stanford called the login cross-site request forgery attack. And the idea is that when we go to the web attacker's website, rather than trying to transfer money out of your account or do something with your existing session, all the attacker wants to do is create a new session for you. And so the attacker submits this form to the login page of a particular web page, and then you become logged in under the attacker's account. Essentially, it's a CSRF attack, but instead of targeting the transfer page, we target the login page. So now you're authenticated under the attacker's account using the attacker's password. Why would that be a bad thing? So there's a lot of examples that we came up with. One example is when you do a web search, if Google thinks that you're logged in as the attacker, it gets stored in the attacker's search history. So now the attacker knows what you're searching for, even if you're only using the search box in your browser. So this is a variant on the CSRF attack.
How does the browser know, or how does the attacker know that your browsing history?
So the attack is, the attacker knows the username and password for the attacker. They use this web attack so that the user gets introduced to the attacker via some iframe ad or whatever. The attacker silently logs you into Google under the attacker's account. And now the attacker, who knows the attacker's username and password, go to Google, log in, go to the web search history page, and watch as entries start getting added to it. Every time the user does a search, Google thinks that they're logged in under the attacker's web account. So it gets added to the attacker's search history. So this sort of turned our understanding of CSRF on its head, because people used to call it a session hijacking attack or a session writing attack. The idea being that you already had to have a session, and the attacker was just trying to jump in and join it. But what's fundamentally happening here is that the attacker is making a form post, abusing the fact that the form post API in JavaScript is cross-origin, and confusing the web server as to where this request is really coming from. So let me give you a more subtle example of this attack. So let's say you go to a web page that has a PayPal donate button. So this is how a lot of websites make money. Users, out of the goodness of their heart, make a donation. But maybe you only want to donate $5 to kanjiquizzer.com, and you don't want to give away everything that you've got. So you click the donate button, and you get sent to the PayPal login page. In this case, the attacker opened it up in a new tab. So this is nice because the attacker is now sitting here in the background, being a happy web attacker, trying to join into your session with PayPal at just the right moment. So this is actually what it looks like when you're about to make a donation. You're supposed to enter in your username and password, click login, and for a few seconds you see this sort of logging in screen, and then you land on some page that assumes you're a logged in user. So in this case, PayPal wants me to add a checking account to my PayPal account. So let's say I fill in my bank details and click continue. What do you think happens? Well,
The attacker's PayPal account.
exactly. So while this logging in prompt was running, the attacker who's sitting there in the other tab can submit any form request it wants to the PayPal site. So that wouldn't be possible if the attacker didn't have a foothold in your browser. There's something about the attacker being able to do things concurrently with PayPal that allowed this attack to work. And as a result, when the user clicks continue, they've just saved their banking information into the wrong account. The attacker can now log into their PayPal account, which they have the username and password for, and make transactions using the user's credit card. So we've been working with a variety of browser vendors and websites to try to develop better defenses for cross-site request forgery. Yeah, go ahead.
So basically, you assume the user is visiting the attacker page first, or how do you?
Right. So in the web attacker threat model, we always assume that the user visits the web attacker's page. If you don't make that assumption, a lot of the attacks get a lot harder. But we've done these measurements that show that it's actually quite common for users to get introduced to attackers. So we want to make sure that we're securing PayPal against that.
Do you think the problem here is that because these two tabs sharing the session? So should the two tabs share the session?
Well, so I think you're hitting on a good point, which also happened with the Frame example before, which is that there are all these cross-origin APIs in the browser. Frame navigation, form submission, and it's very easy to mess up if you're a website and get hosed by this cross-origin API. So these APIs, I think, are the most important APIs to analyze for security. And unfortunately, I think a lot of them were designed in a simpler era where people were really not interacting with as many principals at a time. So yeah, you could design a browser that didn't have any cross-origin APIs. But a variety of web pages which were designed sometime between 1996 and 2009 might be relying on those APIs. So now you have this dilemma. Do we break existing web pages, or do we allow the current web pages to run, but somehow adjust the protocol so that just the attacks are blocked and different types of legitimate activity are still allowed? And I think that's really something that a lot of the standards bodies are wrestling with right now with respect to this cross-site request forgery attack. They want to find some way that we can still allow cross-origin form posts because so many websites are using them. Every website that adds a Google search box to their web page is using a cross-origin form to connect to Google. In fact, really, you can think of any cross-origin hyperlink as somehow connecting two domains together in a cross-origin way. So people are trying to design a solution to cross-site request forgery that doesn't break the web, but somehow makes this problem of how do you defend your website against CSRF a little bit easier. The way that PayPal is doing it today, they have these secret tokens that are on their transfer forms. And when you click Submit, they check to make sure that the web page that has the transfer details also has the secret token that they put in the original form. If it's not there, they reject the request. It turns out it's quite hard to build a web page that does this correctly. We've analyzed a lot of different frameworks that are trying to do this automatically, and we found vulnerabilities or they leak the token in various ways. So we'd like to come up with something that's a little bit simpler. One thing that I do like is that Rails and other web application frameworks like ASP.NET are building in the CSRF protection into the framework so that each web page doesn't have to solve this problem individually. They can just pick their framework of choice and then get protection automatically. But we've been looking at the refer header as a possible alternative to these secret tokens. Unfortunately, it's not usable over HTTP because of all the blocking that goes on. And we didn't really know that until we ran our experiment to see just how bad it was. But now that we know that blocking over HTTP is really bad, the silver lining is that over HTTPS, refer accuracy is very good. And so if PayPal wanted to prevent this login CSRF attack, they could do it with only a few lines of code by essentially just doing refer checking on their login page. They wouldn't even have to implement a secret token defense because their site is served completely over SSL. All right. So I talked about a few examples of things that we've worked on at Stanford to try to take the basic web attacker threat model. The attacker just gets an introduction and see what kinds of attacks we can find and then work with vendors to deploy a solution. But sometimes the web attacker threat model isn't strong enough to describe the attacks that we're worried about. So I'd like to give a few examples of where web security research departs from the web attacker threat model. So one thing that you might be interested in is the attacker is like a rogue network access point. Or the attacker is someone who's sitting next to you at Starbucks. And you might want to protect your sessions with websites against that kind of attack. It's very hard to do this with basic HTTP because HTTP was not designed for security against the active network attacker. But you may be able to protect yourself if the website's using SSL. We found a bunch of attacks on sites that use HTTPS, ranging from mixed content vulnerabilities to problems with cookie integrity. And we've been proposing solutions that try to make it easier for websites like PayPal that want to do everything over SSL to protect themselves against these active attacks. But it turns out to be a deceptively hard problem. So that's one thing you might do, is essentially give the web attacker also the ability to corrupt your sessions with the website. But the attacker still gets to live in a separate tab and be running JavaScript code simultaneously with while you're at the SSL site. And that turns out to be very important for some of the attacks. So another thing that you might want to give the web attacker, and this is a threat model that I think Helen's very interested in with the Gazelle browser, is an attacker knows about a vulnerability in your browser. But luckily, the vulnerability is somewhere in a sandbox part of the browser. And so how do you design the browser such that the attacker who knows about a vulnerability still can't bypass the browser's security policies and do bad things like install malware on your system, read all the files on your system, or even bypass the same origin policy and connect to other sites? So there's been a lot of work in doing this. I worked on the Chrome project at Google, which was trying to focus on, our initial version of it was really focusing on protecting your file system from being read or written by a website that found a vulnerability in your browser. But I think there's a lot of work in trying to go even further and enforce more of the browser's same origin policy in some sort of privileged component under the theory that most of the vulnerabilities live in the image renderers or the HTML, JavaScript engines, which have most of the complexity of the browser. Essentially building the browser like an operating system, where you have a small privileged component that's the trusted computing base, and then a large component that has all the complexity of the web. So it's important that the attacker be able to get onto your system. And so I think the introduction aspect of the web attacker is a very important part of analyzing the effectiveness of these solutions. Another example that we've been looking at is the web attacker gets to have a widget in your mashup. So the user knows that this widget is controlled by the evil gadget guy. And they're fine with that as long as it lives within its little rectangle. And the web attacker shouldn't be able to affect all the other components of your mashup. So iGoogle is a very canonical example of a mashup, but you can think of really any ad network that serves ads and iframes as a form of mashup, because they're bringing together content from multiple sources. So how do you do things like design a communication scheme where the integrator, Google in this case, can talk to the evil gadget without being attacked by all the other frames? So Microsoft designed a protocol that does this using fragment identifier messaging. And the idea is that you attach messages to the end of URLs. And because the navigation API in browsers is cross-origin, this works even if you're sending a message to an iframe that's been put in a throwaway domain. So this allows you to build a mashup that has lots of different iframes. The code is written by lots of different people, but they can still communicate using these messages. So the key thing about navigation is that you can navigate a URL, but you can't read the URL of a cross-origin frame. It's a write-only API. And when you navigate, you get to know what URL you're sending it to, including the domain. So you get confidentiality. If you ever set the URL of a frame, you know that it's only going to be readable by the origin you're trying to send a message to. However, there's no authentication. There's no way using basic fragment identifier messaging to know where you got a message from. It could have come from anyone. It doesn't say in the message in any sort of secure way, this message was sent to you by the integrator. So it's kind of analogous to having your messages being encrypted with a public key. So IBM tried to build something like this. Microsoft also tried to build something like this. And they were essentially trying to add authentication to the existing confidential API. Some way of essentially figuring out where a message came from using a multi-stage protocol. So we looked at Microsoft's protocol. We had to reverse engineer it a little bit. And we found that it was very similar to the Needham-Schroeder protocol for network communication. Unfortunately, there's this anomaly in the Needham-Schroeder protocol. It basically says if the good guy ever tries to initiate an interaction with the bad guy, then the authentication property of the protocol can be broken. And there was an analogous attack on Windows Live channels that did exactly that. So here's an example. You have a gadget that thinks it's talking to the integrator, but actually it's talking to another gadget in the same page that was written by someone other than the integrator. So we proposed a fix to the protocol that's based on the Needham-Schroeder low protocol. And this got adopted by both the Smash team as well as the Windows Live channels library. So that's an example of where we took the web attacker and we gave them something else, a foothold into the mashup. And that ended up being very useful for finding an attack that otherwise wouldn't work. I should note that there are certain threat models that don't even make sense for analyzing the Windows Live channels. For example, Windows Live channels is not designed to resist a network attacker. So a network attacker could potentially fake messages to the integrator, and you'd never know, because that's not part of what the protocol is trying to do. But if you pick the gadget threat model, where the attacker gets a gadget in somebody else's mashup, then you can actually find this attack. So fragment identifier messaging is kind of a hack. We've been advocating for a new protocol that adds support for cross-origin communication natively. The idea is that if you want to send a message from one frame to another, whether it be in a different window or the same window, all you have to do is just call the PostMessage method of this frame and specify whatever your message is. And then the browser will let this guy know where the message came from. So unfortunately, the original PostMessage proposal had a problem. It didn't really provide confidentiality. It had the reverse problem that fragment identifier messaging had. So you could send messages, and you'd know exactly where the message came from. So there was no problem with that. But when you received a message, there were attacks where, using frame navigation, the attacker could jump in and receive your confidential message without you intending it. So we wrote a paper at Microsoft that was describing a communication mechanism between origins called Mashup OS. And Mashup OS COM request primitive, which was for communication across origins, had this second argument where you specify the origin that you were trying to send the message to. And so what we did is we proposed that PostMessage adopt this second argument. So when you send a message, you're not only saying what you want the message to be, but also who you want it to be received by. And luckily, we got this just in time before it was adopted in Firefox. And so the initial implementation in Firefox shipped with this mandatory second argument. And so now all of the browsers have adopted this, including IE, the second argument that lets you say who you're sending a message to. Yeah?
Circle browser?
Very good question. The question mark in a circle browser is the what working group, which is the Web Hypertext Applications something working group. They are the working group behind HTML5. And this is a standards group that's it's moving very fast, uncomfortably fast for some people, at standardizing a lot of the de facto features that web browsers are implementing that no other working group is taking on. So things like content sniffing in browsers, something that every browser has to do. It's not standardized. It's extremely important for security. And so we've been working with the what working group to try to get those features written down. So at least if you're building a new browser, and by the way, there's been a lot of competition in the browser market lately. So I'm very excited to see that people are interested in building new browsers. If you're building a new browser, you don't have to invent your security policy from scratch. There's a document out there somewhere that tells you all the hairy details of how you implement these same origin policies. All right, so I think I'm running out of time, so I'm going to wrap up. I think the web attacker threat model is a nice basis for research because it separates out the user interface problems of how do you figure out where the user thinks they are, and how do you protect their password that they're entering into the page, from how do you make sure the browser is not confused about how it's allocating the resources that this web page has. Things like your pixels, your cookies, those are problems that really don't require the user, and you shouldn't need a user interface in order to protect those resources. They're completely outside of the user UI problem. So you don't need a user study in order to figure out whether or not you've successfully prevented the attack. What you need instead is an analysis based on what the capabilities of the threat model are to show whether or not it's possible for the attack to work. So I think as the web progresses, we're going to find more and more ways for the attacker to get introduced to the user. I think that we can't necessarily blacklist every bad website on the internet, and these ad networks are going to cause a lot of introductions to happen. And that's good. I think it's good for there to be a very low barrier to entry to get your JavaScript code running in the user's browser. But there's a responsibility with these cheaper introductions of building a security policy that can deal with all of these different principles that are throwing code into the user system. I think that very slowly we're making progress on the authentication problem. I think there's a lot of promising options out there, things like password authenticated key exchange, card space. I think it's good that people are experimenting with that. I think eventually we'll make some headway on the phishing problem. But as we do, it'll become more and more important that the browser's security policy not be confused, because the user will be less confused. And so the browser will become the greatest point of weakness. And I think that we may not use exactly the weakest threat model web attacker that I introduced at the beginning, but we'll keep giving the attacker some very minor tweaks to their capabilities. Maybe give them an introduction into a mashup like I showed earlier, or some know about some bug in the browser. So we're going to keep tweaking the threat model, but this cheap introduction I think is going to remain the same. And that's why I think this is a good way for thinking about web security, rather than just assuming the user will only go to good websites. So that's my research talk. Any questions? You guys have been a really great audience. Thanks for the questions. Yeah.
Do you think kind of, I'm stepping back. Do you think the web is getting more secure or less secure?
I think the web is getting more useful, and I think that that is ultimately what matters. People.
That's not the question I asked.
So if you look at what is happening with fraud, as a percentage of web transactions, it's been going down, even though it's on the rise. So I talked to a lot of guys at the anti-phishing working group, and
How do they know these things?
well, so the credit card companies often feel a lot of the fraud themselves because they eat it, and they want to eat it. That's their business model. When someone's credit card number gets used in a malicious transaction, the user complains. The credit card company's job is to pay for the damage. They try to push it off onto the store owners as much as they can, but they keep very good logs of what's going on there. So they're the ones who know, web fraud is something like a nickel out of every $100 that's going on the web, which is actually nothing compared to the fees that Visa charges you with every transaction. So it's under control. I think the web is becoming more useful. I think that attacks are still on the rise. And if you look at certain types of web attacks, things like malware resulting from websites getting hacked via SQL injection, there are particular sectors that are growing at really alarming rates. And so I think that there's going to be a lot of work to do for web security researchers for many years to come. But I'm perpetually an optimist that the web is going to continue to be used as a platform for building really interesting web applications. We'll probably see a lot more native code running. I know there's been a lot of proposals to do this. So the web browser is going to become a more powerful primitive, but the idea that you can go to a web page and the web page lives in a sandbox that doesn't have complete control over your computer, I think is an extremely powerful way to build websites. And it allows users to interact with people that they don't trust quite as much as they would if they wanted to install a program onto their local system. So I think it's really good that browsers are being used, because the alternative of just downloading arbitrary code from people and running it is really bad.
What do you think some of the main pain points in today's web applications that's actually preventing the web applications making the, to be the same as desktop applications, to be treated the same, to evolve to desktop? Well, what do you think the major hurdles for web applications?
Can you repeat the question?
So the question was, what are the main hurdles for web applications for them to offer near to desktop experiences and be as powerful as a desktop application? So I guess there's two approaches to that question. You can ask, what are the development challenges, or what are the security challenges? I think that as a web application developer, there's a lot of trivia that you need to learn in order to build a secure web application. And you're constantly going to be running up against different security restrictions in browsers that prevent you from doing things that you want, like uploading files from the user's file system, going into full screen mode, lots of things that you can't do for security reasons. So I think there needs to be some way to solve that problem. And I think that one approach that you might want to take is to really focus on these frameworks, things like ASP.NET and on Ruby on Rails, that will solve all of the uninteresting, trivial web problems, things like cross-site scripting and cross-site request forgery, so that the web developer doesn't really have to think about that. They can code in a higher level language that allows them to abstract away all of the details of the way that web forms work and the way that JavaScript works. And so there's been some effort in this direction, but I think you still see a lot of people hand coding web applications. So there's a lot more work to do.
Do you think we have the solutions to those problems today? Do you think those are trivial problems that we already know the answers to, or you think
I mean, you look at problems like SQL injection. We know the answer to SQL injection, right? Use parameterized SQL. But somehow this is the biggest source of vulnerabilities on the web. And a lot of it has to do with the fact that legacy web applications make up the majority of the web. And so we need to provide a solution for those people, or we need to provide really, really powerful frameworks that encourage them to go rewrite their application because it's just so easy to do that. And I think that we're making progress. It's not as fast as I'd like, but that is happening. Yeah, Stuart?
So one of the problems with frameworks is that if you're lucky, the people who wrote them have done everything you need underneath, but they're not always anticipating what you're doing.
That's right.
And so you no longer understand whether you're getting certain protections or under what circumstances, if you want to modify the framework in some way, that you will no longer get those protections. And whatever you provide in a framework is always going to be some delta behind the cutting edge.
That's right.
Because you can never ship a framework at the same rate as the people who are on the cutting edge.
Yeah.
So I find the framework, there's something fundamentally unsatisfying about solving things in the framework, because you still have this horribly complex system underneath that is very brittle, that you're hoping holds together because of this framework.
Yeah.
Can't have like a Windows update mechanism where we know our cross-site scripting API is messed up. There's some flaw in it, and then a couple weeks down the road we make a fix for the API, and anyone that's using the framework gets a notification saying, hey, this API has changed. If you want to accept the risk of taking the patch.
And thanks to all the complexity underneath below, we never know what happens when you get that change.
Right. But I'm saying that way, like, 'cause I think one thing that's really difficult is what you said, where there's so much trivia and security is so complicated. Even a security engineer doesn't know all the little things that they need to do.
Yeah.
So how do we expect a developer to understand all the nuances that they have to follow to create a secure website? You can't do that. You can't do that for them.
Yeah, I mean, I definitely think that the complexity is slowly getting out of control. Browser vendors are constantly under pressure to add new features. They want to make the web more usable, closer to desktop experiences. But with each new feature that they add, there's the risk that it's going to create some pitfall for a website to fall into. And so you can't really treat the web as a static platform. Oh, we'll just fix all the bugs, and then everything will be perfect, and we can build a really awesome framework on it. The web is going to always continue evolving forward. People are going to start using plugins. They're going to use different types of technologies. And we have to treat it as a platform that does adapt over time. I think it's possible that you could have it adapt in a way that it actually gets simpler to reason about. There's been some efforts to do this. I'll call in you in just a second. Just to finish my thought, there's been some efforts on content restrictions, for example, are a way for you to basically just say, clean slate, I want you to get rid of all these features that I'm not using so I don't have to worry about whether I'm using them wrong. And let's bring the web page back to sort of a simpler web where there are only a few things that can happen, and those are the features I know that I'm using. And you can declare as a website what features you actually want out of the browser. So there's been some effort to get that deployed. There's a lot of complexity in building a content restrictions system that makes sense, but I think there is some hope in that regard. Yeah, John?
So a web developer today is trying to write a program that runs on this dynamic client that's changing when the rules are changing out from under the developer. One can also write a server-only program, right, where you log in with a telnet session or with a PNC session or something. And do you think that writing web applications is strictly harder than writing a server-only application? I mean, it seems like the web has all these anomalies. The web application programming model has all these anomalies that make it sort of strictly harder than writing the server piece of it. Is that
care about
fundamental?
security.
What's that?
If you care about security.
If you care about security, that's what I mean. And is it fundamental, or I mean, or it might be that it's fundamental, meaning that even if we restricted you to writing telnet-only applications, you'd still have all these same problems in the end. Yeah. Or maybe that there's something just wrong about the way the web evolved, and if you look at it the other direction and say, well, no, we know how to write server applications in a way that's not intractable, so why don't we come at it the other direction and try to make writing web applications more like writing server applications?
I think what that is going to end up doing is pushing a lot of the security problems of the web onto the server where you have to solve them again.
So it's the same problems, just on a different machine.
Yeah.
I disagree. I think it's different. I think when you write a server application, you're just concerned with the security of the server. When you write a web application, not only do you have to be concerned about protecting your server, you also have to be concerned about attacks that are going to occur on the client. So I think that's the difference between, let's say, a telnet application and a web application.
Yeah, I mean, I think you're both right. There is some amount of fundamentally difference about the way that the browser works versus what a server could do if it knew that it was isolated. But there are a lot of interesting problems about delegation. Let's say I want to know whether or not you're signed in at Google in order for you to use ORCID. Well, if they're completely isolated from each other, it's really hard to do that. Right. So if you're going to have to solve that problem anyway, you might as well have everyone solve it the same way instead of solving it in 10,000 different ways on the server.
Well, I think the lines are blurring anyway. If I write a web service, is that intended to be consumed by another machine, or is it intended to be consumed by a browser?
Right.
Well, you don't know.
Agreed.
I mean, so
you have to go to the lowest common denominator.
Exactly.
And so when you write a telnet application, I'm not worried about another telnet application attacking the telnet application that my user is going to be using.
And in this process, you've lost all the interesting functionality that the web has invented.
Right.
This cross-principal service composition. I mean, but it doesn't necessarily be the case that this functionality comes at the cost of security. I think
Agreed.
It doesn't have to be that case.
It should never be the case. I think you should never lose functionality for security.
Yeah, if we understood the web security model well enough, we might actually be able to do that. But it's still sort of being revealed as we go. Anyway. All right, thanks everyone.
Great, thank you.